In this next example, we have a much more complicated circuit consisting of a 15-volt battery connected to many resistors. We are first asked to find the equivalent resistance of all of these resistors. Before I begin combining resistors in series and parallel with each other, I will first redraw the circuit. The circuit I drew down here is exactly identical to the original circuit that we were given. In other words, when I say a circuit is exactly identical, I mean that all the connections between the circuit elements are the same. Here we have a 2.4 ohm resistor. One side of that 2.4 ohm resistor is connected to a 6 ohm and a 9 ohm resistor. The other side of that 2.4 ohm resistor is connected to a 6 ohm and a 6 ohm resistor. Here's the 2.4 ohm resistor. One side of this 2.4 ohm resistor is connected to a 6 ohm and a 9 ohm resistor. The other side of this 2.4 ohm resistor is connected to a 6 ohm and a 6 ohm resistor. All of the connections in the circuit down here are identical to the connections in the circuit up here. Pause the video and convince yourself that this circuit is exactly identical to the circuit up here. The reason I chose to take our original circuit and redraw it before combining anything is I can very quickly look at this circuit and identify which circuit elements are in series or in parallel with each other. That is trickier to do for the circuit as it is originally drawn. In the next video in this playlist, you will see another method for determining whether circuit elements are connected in series or in parallel with each other. Because we will have multiple steps in combining resistors in series or in parallel before we find a single equivalent resistor, it will help me to have the circuit drawn in this manner. Comparing these two circuits, I could see that the 6 ohm resistor over here is the same as the 6 ohm resistor over here. We have a whole lot of 6 ohm resistors in our circuit, so I'm going to color code these resistors to help me keep track of them. I will put this 6 ohm resistor inside a purple box, and I will put this 6 ohm resistor inside a purple box. The 6 ohm resistor over here is the same as the 6 ohm resistor over here. I will underline this 6 ohm resistor in red. And the 6 ohm resistor here is the same as the 6 ohm resistor here. I will double underline these resistors in blue. Again, I am only denoting these resistors to help me keep track of them. When you're working through a problem, you could choose different colors of ink if you have several resistors that all have the same resistance in a circuit. So if I look at the circuit that I have here, I see right away I have a 6 and a 9 ohm resistor in parallel with each other. So I will combine these two resistors first. Because I have two resistors there in parallel with each other, I could say that the equivalent resistance of these two resistors would be given as 1 over R equivalent is equal to 1 over 6 plus 1 over 9. Looking for a common denominator, 1 over 6 could be written as 3 over 18, and 1 over 9 could be written as 2 over 18. So this is 1 over R equivalent on the left-hand side, and 3 plus 2 gives me 5, so I have this being equal to 5 over 18. Since 1 over R equivalent is equal to 5 over 18, I could say R equivalent for these two resistors in parallel is equal to 18 over 5, which is equal to 3.6. So I could combine these two resistors into a single 3.6 ohm resistor. My circuit now looks like this, where I have a 3.6 ohm resistor replacing the 9 and the 6 ohm resistors that were in parallel with each other. Looking at the circuit now, I recognize that a 2.4 and a 3.6 ohm resistor are in series, so I will combine these two resistors next. The equivalent resistance of these two resistors will be the sum of their resistances. So I could write R equivalent is equal to 2.4 plus 3.6. Therefore, the equivalent resistance of these two resistors in series is equal to 6 ohms. When I redraw the circuit with these two resistors combined into a single 6 ohm resistor, I then immediately see that I have two 6 ohm resistors that are in parallel with each other. These will be the two resistors that I combine next. These two 6-ohm resistors could be combined into a single equivalent resistor whose resistance is given as 1 over R equivalent is equal to 1 over 6 plus 1 over 6. Then solving for R equivalent, I find R equivalent is equal to 3 ohms. After I redraw the circuit with the two 6-ohm resistors in parallel combined into a single 3-ohm resistor, I'm left with a circuit consisting of 3 resistors in series with each other. I could find the equivalent resistance of these 3 resistors in series by adding their resistances. So the equivalent resistance of these 3 resistors would be given as 6 plus 3 plus 6. Therefore, I will be left with a circuit consisting of a single 15-volt battery and a single resistor of resistance 15 ohms. We will now calculate the currents flowing through each of the resistors in our original circuit. Here's a picture of our original circuit with the currents drawn in. Current I1 is the current that flows through the battery and the two 6-ohm resistors immediately connected to the battery. Current I2 is the current flowing downward through the 6-ohm resistor that we designated with a double blue underline. Current I3 is the current flowing through the 2.4 ohm resistor. Current I4 is the current flowing diagonally through the 6-ohm resistor we designated with the purple box. And current I5 is the current flowing through the 9-ohm resistor. To begin, let us look at the circuit with the single battery and the single equivalent resistor. Looking at this circuit, we could see that there will be a voltage drop of 15 volts across the resistor. If I have a voltage drop of 15 volts across the resistor, I could use Ohm's law to find the current that is flowing through this circuit. I could write V equals IR, and therefore I find 15 is equal to I times 15. Therefore, I could find that the current flowing through this circuit is going to be 1 amp. Comparing this circuit to my original circuit, I could see that the current flowing through the battery here will be the same as I1, the current flowing through the battery in this circuit. Therefore, my current I1 will be 1 amp. Just like in the previous example, we will gradually unpack our circuit. So our next step in solving this problem is going to be break this 15 ohm resistor into a 6, a 3, and a 6 ohm resistor. Looking at this circuit, because I still have a single loop, I expect the current flowing through this circuit to also be 1 amp. So this current is going to be 1 amp. Now using Ohm's law, V equals IR, I could find the voltage drop across the 3 resistors. I have a 6 ohm resistor with a 1 amp current flowing through it, so there will be a voltage drop of 6 volts across this resistor. A 3 ohm resistor, current of 1 amp again flowing through it. I'll have a 3 volt drop across this resistor, and the 6 ohm resistor down here will have a voltage drop of 6 volts across it. Now that we have all the information with regard to the resistance, the currents, and the voltage drops across the 3 resistors, we will unpack the circuit one step higher up. We will break this 3 ohm resistor into 2 6 ohm resistors in parallel with each other. When I draw the circuit again with the 3 ohm resistor broken into 2 parallel 6 ohm resistors, I'll have a picture that looks like this. We have the 1 amp current that's flowing through the battery and the 2 resistors immediately connected to the battery. And we have the 2 6 ohm resistors in parallel as opposed to the single 3 ohm resistor. The voltage drop across resistors in parallel will be the same for each of those resistors. Therefore, there will be a voltage drop of 3 volts across both of these 6 ohm resistors in parallel. I could find the current flowing through these 6 ohm resistors in parallel using Ohm's law, V equals IR. I would have 3 is equal to I times 6, therefore I is equal to 1/2. Looking at this picture and comparing it to my original picture, I see that the 6 ohm resistor I designated with the double blue underline is the resistor that has current I2 flowing through it. Therefore, this current is going to be current I2, and I could say I2 is equal to 1/2 amp. Another way I could figure out the amount of current flowing through these resistors is to just look at the picture and reason that if both of these resistors are identical, then half of the current should flow through one resistor and half of the current should flow through the other resistor. Therefore, if I have a current of 1 amp reaching the junction, I should have half an amp of current flowing through each of these resistors. Now let's look at our original circuit. Specifically, let's take a look at this junction of wires right here. If I look at this junction, I see that current I1 is flowing into the junction and currents I2 and I3 are flowing out of the junction. If we demand that the total current entering a junction of wires must be equal to the total current exiting that junction of wires, because we don't want charge building up anywhere in our circuit, that implies I could write that I1 should be equal to I2 plus I3. We already have numerical values for currents I1 and I2. So I could write 1 is equal to 1/2 plus I3. And this implies that current I3 will be equal to 1/2 amp. In order to solve for current I4 and I5, our goal will be to determine the voltage drop between this point in our circuit and this point in our circuit. So we will again unpack our circuit one step further and solve for the currents and the voltage drops across the resistors in that circuit. When we unpack our circuit one level further, we will break one of the 6 ohm resistors into a 2.4 and a 3.6 ohm resistor in series with each other. Because we know the current that is flowing through these resistors, 1/2 amp, we could use Ohm's law to find the voltage drop across these resistors. So I could say V is equal to 1/2 times 2.4, and I find the voltage drop across this resistor will be 1.2 volts. So here, voltage drop is 1.2 volts, and V is equal to 1/2 times 3.6, which is 1.8. Therefore, the voltage drop across this resistor will be 1.8 volts. We will now break this 3.6 ohm resistor into a 6 and a 9 ohm resistor in parallel with each other. We then arrive at the circuit that we began this problem with. I omitted many of the currents flowing through this circuit. They are still there, but I decided to not draw them just to keep the picture neater. When we expand a 3.6 ohm resistor into a 6 and a 9 ohm resistor in parallel, the voltage drop across the 3.6 ohm resistor will be the same as the voltage drop across the 2 resistors in parallel that it is expanded into. So since there was a 1.8 voltage drop across that 3.6 ohm resistor, there will be a voltage drop of 1.8 volts across the 6 ohm resistor, and there will be a voltage drop of 1.8 volts across the 9 ohm resistor. I could then use this information and Ohm's law to find the current flowing through these 2 resistors. For the 6 ohm resistor, using V equals IR, I could say 1.8 is equal to I times 6, and I find that the current flowing through the 6 ohm resistor is going to be 0.3 amps. Using V equals IR again, 1.8 is equal to I times 9, and I find that the current flowing through the 9 ohm resistor is 0.2 amps. Comparing this picture to the circuit we have drawn here, I recognize this current as I4 and this current as I5. So I could write these down, 0.3 amps and 0.2 amps, and therefore I have found all the currents in the circuit.